One of the key elements of the reactive manifesto is that reactive systems have to be built on a message-driven architecture. That is the foundation of a reactive system, and it's what allows the system to be reactive. But what does that mean to have a message-driven architecture? So reactive systems put an emphasis on what we call asynchronous non-blocking messages. Now, these are messages that are sent without waiting for a response. That means that essentially you take the message, you send it to the receiver, and then you walk away. You don't sit there and wait for an acknowledgement from the receiver saying that they've got it, they've processed it, whatever. You just send the message and walk away. Now, you may be interested in a response. This is not to suggest that you aren't interested in the response, but we allow that response to come asynchronously. And again, if we think about this in terms of people, this is the equivalent of you sending a request to a teammate saying, hey, could you please complete this task? And then you go on and you continue to do your work without waiting for a response from that other person. They may respond to you at some point and say, no, I can't do that. Yes, I can do that, and here's the results. They may have any number of responses, but those responses will come later. You don't know when later because you don't know when they're going to get around to reading your message. So that's really the nature of an asynchronous non-blocking response, an asynchronous non-blocking message. And the key to this is because when you send that message, you walk away and continue to do other work, it means it allows you to free up resources. Again, if you are dealing with people, if you stand over somebody's shoulder and wait for them to finish the task that you've asked them to do, that's very inefficient. But if you walk away and continue to do your work while they do their work, now you've got a parallel process, and now you're being much more efficient. And that's what we're aiming for here. We're aiming to avoid this situation where two parts of the system are waiting on each other and you're consuming resources the entire time. So what are the advantages to asynchronous and non-blocking messages? A big advantage is that resources like threads, memory, things like that can be freed immediately. So you send the request, and then you move on to something else, which means you can potentially release the thread rather than holding on to it. If you had to hold things in memory related to that request, you can drop those things out of memory. So you can start to free up your resources. It also means that there's less contention. In other parts of the Lightbend Reactive Architecture training path, we talked a lot about how contention affects your scalability. When you are sitting there using up a thread, using up memory, things like that, you have contention for those resources, and that reduces your ability to scale. So by eliminating that contention or reducing that contention, it allows us to scale more. The other thing too is that it also helps us with reliability. So if, for example, the external service that we are sending a message to is down, it may not be available at the time. Now, if we are doing a synchronous request where we're actually waiting for the response, when that system is down, we send the message and then we fail because that system is down. So that reduces our reliability. On the other hand, if we do this asynchronously, what it allows us to do is it allows us to put that message into a queue and then deliver it whenever that service comes back online. We already know that the message is going to be delivered at some point, and we don't care when that point is. So we can just drop it in a queue, and as soon as that service comes back on, back online, we will deliver it. This gives us a higher rate of reliability. And one of the things that it allows us to do is to have portions of the system go offline for a period of time and have the remainder of the system to continue to operate as normal. So that's a very cool thing that it gives us with reliability. So that tells us a lot about the benefits that we get out of building a system with asynchronous messages. But what about synchronous messages? Now, in a reactive system, asynchronous messages should be your backbone. This basically means that you should try to build using asynchronous messages wherever possible. Synchronous messages can be used, but keep in mind that sometimes we can relax the requirements of those synchronous messages. So rather than sending a message and waiting for a response saying, you asked me to do something and it's done and here's the results, we might just send a message and have the receiver acknowledge that they got the message and basically say, yes, I got that and I will complete it eventually. that may be sufficient in a lot of cases. This is the equivalent of sending a request to your coworker and saying, hey, could you do this task? And having your coworker reply back and say, yes, I heard you, and I will do that task, but I can't get to it now, I'll get to it later. That may be all you need. You know that they've got the message, you know that they'll get to it at some point. You can now forget about it for a little while. You don't have to sit there going, hey, did you hear me? Hey, did you hear me? Hey, did you hear me? You can move on. So you may be able to relax the requirements of your synchronous messages sometimes. The key, though, is that synchronous messages, or the need for synchronous messages, should be driven by domain requirements rather than technical convenience. Technically, it's often very convenient for us to build using fully synchronous messages. It's easier to do, but there's costs associated with it. Those costs show up in the forms of inability to scale, reduced reliability, and a number of other things. So even though it may seem technically easier, in the long run, it really isn't, because we end up paying that price in other ways. Our best practice that we would recommend is to use asynchronous by default. So when you're building your system, start asynchronous. Fall back to synchronous messaging only when you're forced. So when a domain requirement comes up that says, we really need this message to be synchronous, okay, then we'll go and we'll fall back to using a synchronous approach. But when we do that, it's very important that we understand the consequences of that choice. Understand that by making it synchronous, you are going to introduce potential problems related to scalability, related to reliability, and a host of other things. So when we make that choice, recognize those consequences so that we can figure out how to minimize their impact. Now, as I mentioned, synchronous messages and a synchronous approach often seems easier technically, and in many ways it is, because there are costs to using asynchronous messages. So let's talk about what some of those costs are. So in a monolithic architecture, if you go to a traditional monolithic architecture, coordination and consensus building is often done using database transactions. So if you have multiple pieces of the system that you need to update, you open a database transaction, you update multiple tables, then you commit the transaction and you're done. That's how you would typically do it in a monolithic architecture. In a distributed system, though, this gets more difficult, especially when you're using asynchronous messages, because now what happens is your application is spread across multiple microservices, and those are all communicating asynchronously. Trying to open a transaction when you're potentially accessing multiple databases doesn't actually really work. And even if you could do that, because of the nature of the asynchronous messages, you'd have to hold that transaction open for potentially a long period of time, which makes things very brittle. So we want to avoid that. We want to avoid long-lived transactions that cross multiple microservices. So the question then becomes, how do we do that? How can we avoid long-running transactions that span multiple microservices? And we'll get into how to do that in the next part of this course.